Here, today we'll learn eigenvalue analysis of a structures. Especially, we'll learn eigenvalue analysis of composite structures. If you learn eigenvalue analysis of composite structures or composite plate, it will be easy for you to go for eigenvalue analysis of isotropic plate, and it also will be easy for you to go for eigenvalue analysis of a beam or other type of structure. So in today's class, we will learn how to get your frequency and mode shifts to eigenvalue analysis. This analysis also known as modal analysis. Before going to that modal analysis, we should know what is the eigenvalue and the eigenvector. So first we learn what is the eigenvalue and eigenvector for a matrix, and then we try to correlate that eigenvalue eigenvector analysis for our civil engineering problem. So we know that eigenvector is a special vector. Eigenvector is a special vector when it operate on a matrix. When it operate on a matrix, so eigenvector is a special vector. When it operate on a matrix, the matrix would be square matrix. Square matrix. When it operate on a square matrix, it is to give the same. It is to give the same vector, same eigenvector with some multiplication constant. So it is to give the same eigenvector with some multiplication factor. Okay, so if we find a vector such that when it operate on a matrix, it to give the same vector with the constant, we used to say that that is the eigenvector of that matrix. And the multiplication factor that multiplication factor we know as your eigenvalue. Okay, so x is here eigenvector, x is your eigenvector, and lambda is your eigenvalue. What is happening here? Here you can see the vector which has initial direction in this direction. Okay, if you consider the x and y coordinate systems, okay, you try to realize that we have a vector like this. Vector in the sense we have some x and y value, here also some x and y value, x1 y1 and x2 y2. Okay, now it has some direction like this. So when this vector operate on a matrix, it is to the same vector with some magnification factor. So this vector may enlarge in this direction or it may shorten in this direction. Okay, either it can go enlarge in this direction, either it can go in this direction, or it can shorten. So basically, its magnitude can change, but the direction will remain same. So direction will remain same even after it operate on a matrix. Even after it operate on a matrix. Okay, so basically, we are trying to find that eigenvector of the structure matrix when it operate on our mass and stiffness matrix, it always remain the same with some magnification factor, that is your eigenvalue. So in our structural problem, we will observe that we are dealing with a two matrix. Here we have learned that what is the eigenvalue and eigenvector of a single matrix, but our structural problem deals with the two matrix, stiffness matrix and the mass matrix. So here what we are trying to do, here we are trying to find a vector when it operate on mass as well as stiffness, it is to give the same eigenvector with some constant, okay, or with some multiplication constant. Okay, so this is the way we have to basically visualize a eigenvector. So before going to that eigenvalue analysis, let us discuss what is our dynamic problem. So dynamic equation of equilibrium, we used to write dynamic equation of equilibrium, we used to write as a mu double dot plus cu dot plus ku will ft, or some book they used to write mx double dot plus cx dot plus kx is equal to ft. Okay, where x is a function of time, x dot, that is velocity, is a function of time, and acceleration is also function of time. So This is our equation of motions. This equation of motions can be for beam or plate. It depends upon how you are writing the matrix, how or for which structure you are writing the matrix. It can be plate problem, it can be beam problem, it can be any civil engineering problems or mechanical engineering problems where you are representing the physical property in some matrix form in mass matrix, stress matrix, and damping matrix. Okay, so how you want to represent a physical systems in matrix form, depending on that, it will give the eigenvalue of that systems. Yes, for our civil engineering problem, it will be our beam, plate like things or some complex geometry problem. Okay, so here this is our equation of motion where mx double dot plus cx dot plus kx is equal to ft. Now, when we talk about our eigenvalue analysis or modal analysis, we used to say that is our free vibrational analysis. Okay, that we used to say it is a free vibrational analysis. A free vibrational analysis means that vibration in which we do not apply the force, in which the vibration is not a function of force. Okay, so if the structures, if the vibration of a structure is not function of force, in that case we can write our equation of motion in this way: mu double dot plus u plus ku is equal to 0. So these equations we have to solve. Now, thing is that if we are going to solve this equation, in that case, the damping terms basically damping term basically need a mathematical problem. Not mathematical, damping term create a problem for us. So if damping present in the systems, and if we want to find the eigenvalue and eigenvector of the systems, in that case, our eigenvalue and eigenvector is to come as a complex value. Complex value. Come as a complex value. So our eigenvalue will be a complex number, and your eigenvector also will be complex number. If eigenvector become a complex number, in that case, it will be very difficult to realize how the our mood shapes or vector look like. If eigenvector become a complex number, in that case, it will be very difficult for us to judge how our mood shapes, that is our eigenvector, look like. So as engineer, it will be very difficult to judge. Now, as engineer, we need a real valued eigenvector or real valued mode shapes. Mode shapes where all the value or all the magnitude will be real value. So to achieve that, what we used to do, we used to neglect the damping. So damping terms we used to neglect. Okay. One more thing you will realize that damping term do not affect our frequency. Damping term do not affect our frequency much. So here you can realize that omega d, that is equal to 1 omega into root under 1 minus chi square. Omega into 1 minus chi square. Okay, now here you can see this omega is your damp frequency. Okay, now here you can see if we consider 10% damping, which is sufficiently large, if you consider damping as 10%, which is sufficiently large, in that case, our omega d, that will be omega into 1 minus chi square. So here you can see omega root under 1 minus chi means 0.1 and 0.1 square. So omega d that into 1 minus 0.00 0.1, 10% is point, so 0.01 square. Okay, 0.01 square. Okay, 0.01 square. So now here, if we calculate it, that omega d, that will come to omega d, that will be root under 0.99. So if you take square root of it, it will come your omega d, that is equal to 0.9945 your omega. So here you can see, though we are considering damping as a 10%, which is sufficiently high, in that case also our damp frequency and the natural frequency, or damp natural frequency and the natural frequency are very close. Okay, damped natural frequency and undamped natural frequency are sufficiently close. So here we can see the damping term do not affect our frequency in a greater way. So what we can do, we can neglect the damping. Okay, we can neglect the damping, and we also can neglect the force, since it is our free vibration case. Free vibration means we are not considering that our structure is subject to force. In real life, what we used to do, in real life, we used to basically disturb the structures. We used to apply some force for shorter period. We used to apply the force in shorter period, and then we allow the structure to vibrate, and we capture the response. And from there, we used to calculate our acceleration, and from there we used to do FFT, and then we used to see how is the frequency and how is our mode steps. Okay, so in real life, we used to disturb the structure by applying some force, and thereafter we allow the structure to vibrate. Okay, so that force we are applying for disturbance, that is basically for shorter period, and then we are applying the then we are allowing the structure to vibrate on its own natural frequency and mode shapes. We are allowing the structure to vibrate on its own natural frequency and the mode shapes. Okay, so that thing we are basically representing in this way. If t is equal to 0, and here we are considering damping is 0, because damping term is not affecting our natural frequency in a greater way. Now we will have this equation. We will have these equations mu double dot plus k is equal to 0. Now, if you want to get our eigenvalue, okay, then what we will do, we have to assume u, we have to assume some u, and we normally assume in terms of phi sin omega t or e to the power sin omega t, like that way. Okay, so you can assume u is like that, and if we substitute u into this equation, we will observe that we are getting this equation, that u minus omega square, minus m omega square plus k, in bracket there is a term like this. Okay, now since we have assumed these functions, and we initially assume this is our non-zero term, this is our non-zero term. Okay, this is our non-zero term, so this part should be 0. So this part should be 0. First of all, our omega t cannot be 0, because if omega becomes 0, then all equation will be 0. That means structure don't have any frequency, so that omega cannot be 0. And phi is the magnitude. Again, our magnitude of that functions, if u is 0, okay, that means u also is coming 0. That means it don't have any deflection, so that part also cannot be 0. Okay, so rest of the things we have, that your m omega square plus k is equal to 0. Now what we do, we have to take it, we have to consider this part, and if you want to get this equation done, if you want to get this equation done, or if you want to make it 0, to determine it, we have to make it 0. So if we do the determinant as 0, okay, then what we'll get, that we'll get omega square. Here omega square will be equal to, that omega square will be your k by m. Okay, so this omega square term here is known as your eigenvalue. Now, if you want to take the frequency, then we would take the square root of it. So root under k by m is your frequency. Okay, this frequency normally is to come as a radian. We need to convert it into hertz. We can convert it in this way. Omega is equal to 2 pi f, where f is in hertz. Okay, frequency in hertz, and this omega is to come as a radian. Okay, now what we have learned? We have learned that we can model, if you model a structure in finite element framework, if you model a structure in the finite element framework, so you will get our mass matrix, we will get our stiffness matrix, and we directly put it in these equations. We put this in these equations, okay, and then we'll try to find our frequencies. Once we find the frequency, what we're going to do, we'll analysis is a two-step process. In the first steps, we used to find the eigenvalue. Once we get our eigenvalues, what we used to do, we used to put this eigenvalue into this equation, and we used to solve this equation, and we try to find what is our mode shapes or eigenvector. Okay, so eigenvector analysis or eigenvalue analysis is a two-step process. First step, we used to find the eigenvalue, and second steps, we put that eigenvalue into the equations, and we used to find our eigenvector. Okay, so now here in this class, what we are going to do, we are going to model a plate, which is composite plate, and we will learn how we can model the composite plate using three-dimensional solid element, how we can model the same plate using 2D cell element, and next we learn how we can model same plate using a layer-wise manner. Okay, so if you think of a composite plate used to have various layer of different. We used to have different layer of various material. We used to have different layer of various material. One can be GFRP, GFRP, another can be CFRP, another can be basal fiber. We can have different fiber in different layer. So here we learn how we can model the composite plate using layer-wise manner. Okay. Now once we model it, we should know what is the convergence. That means how we can achieve a converged result, how many elements we should use to get our acceptable result. Okay. So once we decided that okay, this element we will use and this many number of element we will use. Okay. Otherwise, you can say the size of the element we will use this size element. If that means basically what type of element we are using, whether linear element or quadratic element, and how many number of element we want to use. Depending on that, we have to decide that which combination we should use to get our acceptable result. Okay, once we get our converged value, next we will learn how we can apply the boundary condition, how we can perform, and which one we should prefer to match our experimental result. Which one we should prefer to match our experimental result. That thing we'll discuss in this class. Let us go for modeling of composite plate using our finite element software, that is ABAQUS. So here dynamic analysis, in the sense we will conduct modal analysis where we will find frequencies and the mode shapes. So here we will obtain frequency and mode shape of a plate under free boundary conditions, and then we will see if we apply some boundary conditions how frequency and mode shape are changing. So here what we will do, we will create the geometry first, and then we will create the geometry first in the part module, then we apply the property, then we will go for assembly. In the assembly we will see if we have more part how we can assemble it, then we will go for meshing. Thereafter we will apply, thereafter we will go for step. In the steps we will try to perform our modal analysis, then we will submit the job. So since we are using modal analysis, since we are performing modal analysis, in that case we don't have to apply any load. Since we are performing modal analysis, modal analysis is a free vibration analysis. So free vibration analysis means that plate or the structure is not subject to any load. Here we used to disturb the structure and we used to get the frequency of the mode shapes. If you see in the real life free vibration analysis, where we apply small amount of load, or we put up the structure and we try to capture the, we allow the structure to vibrate on its own natural frequency and the mode shapes, and we capture the frequency of the mode shapes. Okay, but in finite element modeling, what we used to do, we used to perform modal analysis where we assume the force applied to the structure is 0. So here we have mx double dot plus cx dot plus kx is equal to 0. So we know that our equation of motion, dynamic equation of motion, is mx double dot plus cx dot plus kx is equal to force. Okay, where x, that is your displacement, x dot is velocity, x double dot is your acceleration. That all are function of time, and force also function of time. Now here we assume that there is no damping in the systems, and then we assume there is no force acting in the structure. So we will have mx double dot plus kx is equal to 0. Okay. So now we'll assume some functions, displacement functions, and we put it there, and then we obtain our frequency and the mode shapes. Okay. So there we used to get the mode shape and the frequency, and frequency that is to wrote under k by m, where k is your stiffness matrix, m is your mass matrix. So like that we used to get our frequency. If you want to know more about the frequency, the mode shapes, please go through my previous video. You will get how we can obtain frequency mode shapes. Okay, there we have solved a simple beam problem, and we have learned how we can get the frequency mode shape of a simple beam. Okay, so here we will go for composite structures. So here modeling of the composite structures using coding may be difficult for many. So here we'll apply. Here we'll use FEM software to get our frequency the mode shapes. So here to model the composite plate, what we will do, we have to first create the geometry, then we have to define the property, what type of property we want to define. In assembly, we have to create instances. In the meshing, we will see how many mesh is required to have converged result, and in the mesh also, the mesh will define what type of element we want to use. Okay, in the property, we have some options whether you want to use it as a composite or you want to use as a solid element or you want to use as a layer wise. So we'll see, we'll learn how we can model a composite in various way. We'll learn one by one. So we'll first create the geometry. So here we'll create part, and initially we'll create 3D solid, and extrusion process we'll use, and we'll choose rectangle option, and here we have to define two opposite corners. So first corner I will define as your, here our plate dimension will use 300 by 400 mm. So here what we will do, we will define the opposite corner, two opposite corners. So minus 200 to the power minus 3, comma minus 150 to the power minus 3, and then opposite corner 200 to the power minus 3, comma 150, comma minus 3. So here our plate size is 300 by 400, like that we can create. And thickness we'll assume as a 10 mm, we'll assume as a 10 mm thickness. Here you can see we have created plate, we have created a plate. Now we can define the property. Here we learn how to define the metal property of 3D. Here we learn how to model a property, how to define a property of this composite plate model using 3D solid element. Okay, so here we'll use this paper. Here we'll use this paper. Okay, this paper, and here if you go down, here you can see this is the property are mentioned here. Here density is 1960 kg per meter cube, Ex 35 GPa, Ey 30 GPa, Gxy 7 GPa, and Gxz and Yz is 5 GPa, and this is 0.25. Okay, so here what we are going to do, we are going to define density, that is 1960, and here elasticity as your elastic material. Then here you can choose your engineering constant options. Okay, laminar options will not be valid here. You have to change to engineering constant. Okay, engineering constant you have to choose. So E is your 35 GP, 35 E9, E2 is 30 GP, 30 E9. That E3 value is not given there, so we will use 20 GPa.
Okay, and you will observe that E3 does not affect the frequency, at least first few modes. Okay, frequency of that first few modes. Okay, so E3 you can reasonably assume very close to your E1 and E2. You will observe that that is not affecting much. Okay, so here is our Poisson ratio 0.15. Poisson ratio also does not affect our frequency much. Okay, G12 is your 7 GPA 7E9, and this is your E9 5E9. This also is 5E9. Okay, so these are the elastic property we are providing as an engineering constant to this 3D model. Now here we will consider solid homogeneous, and we have to consider this material 1. Now we have to assign the material. So this option we will use, and we will assign the material here. It is saying that we are assigning at the section 1, that is your solid homogeneous and material 1. Okay. Now here if you use engineering constant, in that case you have to define your datum. Here you have to define your material orientation. So you can define the material orientation using datum line. Okay, so here if you choose this one, here it is saying that use default orientation. Here you have to see whether your x-axis, that C, you are defining your material property EOX is 35 GPa. So EX would correspond to the or one direction. So here you can see it is showing, here you can see it is showing here, it is showing first direction along this, that is our x direction, this is our x direction, and this is our y direction, that means EY direction or 2 direction, and this is z direction along the thickness. Okay, so we can accept it. If you observe that your orientation is not correct, in that case you can change the orientation along this x, y, x6, axis 1, axis 2, axis 3 in this direction. Okay, so now we have defined it, and now what we are going to do, we are going to go for next module, and here in the mechanical property, elastic, and then here we have Young modulus, isotropic. So here instead of lamina, what we can do, we can choose engineering constant. Okay, we can choose engineering constant here. Okay, and we have orthotropic. Orthotropic, here we have to calculate all the data, and isotropic also have to calculate. So if we want to choose any other things apart from lamina, so we have engineering constant option. So here we can provide the engineering constant. We'll see whether it is running or not. Okay. Here we have two other options, that is orthotropic and anisotropic. But problem is that we have to calculate the D matrix. That you have to calculate the D matrix, and you have to provide the data here. Okay. So you should know how to calculate the D matrix. So you have to learn some course. You have to learn how to obtain the D matrix. Okay, you have to go through some course of composite material, and you have to learn how we can update the D matrix. Okay, so we can choose. We have to select engineering constant. We have to select engineering constant. So here 35 GPE1, E 35 E9, here 30 E9, E3 we have E3 E is not mentioned there. So here we can assume some E3. Okay, we can assume some E3, and then nearly 25 E9, but again see, we are assuming it, we don't know how much E3 it should be. Okay, but one thing we will observe, that E3 will not affect our frequency much. Okay, we'll see one more trial, and we'll see that time we'll change the E3 value to 20 to 30 GPa, and we'll try to see whether our frequency is affecting with E3 or not. Okay, that we'll see. So here we have new 1, 2, that was 0.15. So again, we would assume all other Poisson ratio 0.15, we are considering all. Again, Poisson ratio will not affect the frequency much. Okay, if you observe that how the Poisson ratio and out of plane modulus, that E3 is affecting our result, you will observe that don't have much influence. Okay, so here we can choose some value which is close to our experimental value, close to our original model. Okay, then E3 and Poisson ratio may not be that much accurate, but you can choose some value with some value within a some range. In that case, you will observe that we are getting acceptable result. So G12 is your 7 GPA 7E9, and G23 that is your 5E9, and G12 should be 7 GPA 7E9 and G23 5E9. Okay, so here we have defined the material constant means with a final meshing, and before going to the final meshing we also have to perform our convergence study. So here what we are going to do, here we are going to mesh it by seed by edge. We will use this option to model to create the nodes. We'll use this option to create the nodes. We have another option, that is your global seed value. So here if you select global seed value, we can we can mesh it. But here you can see it is saying that mesh cannot be done in this assembly. We have to select part. So if you select part, here you can select, you can give global size, and you can create the nodes, and we can create the meshing. But here we will use this option to control the meshing. Here what we are doing seed by edge. So we will choose this option and this line. Here you can see we are not able to see opposite side. Here you can see we are not able to see other side. So what we will do, we'll choose this option, wireframe option. So if we choose this way, we can see that edge line, and we can select it, and we can define how many number of element you want to create. So let us consider 20 element. Okay, let us consider 20 element this side. Here we can consider 15 element because this size is 300. So here we will consider 15 element like that. Okay, now we'll go for meshing. You can select it as a default option. You can select it yes. Okay, we can select it yes. And here again, if we click it here, you can see the meshing. So this is the meshing we have created. Now what we are going to do, we will go for mode analysis, linear perturbation and frequency analysis. Okay, that is the way we can perform modal analysis in ABAQUS. Now what we will do, we create the job. We will create the job and we'll see is there any warning or error. Okay, if we find there is no warning, no error, we will submit the job. So here frequency of composite plate. Okay, frequency of composite plate. Now here we can check the data. We can see is there any error or warning. If there is error, ABAQUS will not run. If there is a warning, ABAQUS will run the program, but you have to make sure that the warning that is occurring for your modeling not affecting your result. Now what we are going to do, we are going to submit the job. Here we will check the data, and thereafter we will submit the job. Now job is completed. Okay, data checking is completed. Now you can submit it and run the program. Now job also is completed. Now here we see what are the frequency we have. So now here you can see this is your zero frequency. First frequency mode 1 is frequency 0. Second also is 0. Third also is 0. Fourth also is 0. Fifth also is 0. Sixth also is 0. Okay, so here you can see we have 6 frequency, that is 0, that is corresponding to our rigid body motions. Since we do not have any boundary conditions, so plate will exhibit some rigid body motion that is showing. Okay, so there is nothing to worry, and analysis is not wrong. Okay, till now our analysis is not showing some erroneous data. So that is our as per our expectation. Okay, since we do not apply any boundary condition, it will show our rigid body motion. So here all 6 are rigid body motion. Now here you can see the first mode. First mode is here, it is showing as a bending mode. But frequency is coming 18 GPa. Frequency it is coming as 18 GPa. Sorry, frequency here you can see frequency is coming as a cycle per time hertz frequency. But here it is showing 7th mode, mode 7. So this is your first frequency that is coming 18 hertz, and then is 32 hertz. Then we have 47 hertz, 49 hertz, like that. Okay, so basically we are getting some frequency. Okay, 97 hertz. Now we'll see what is the our expected data. Expected data, it is saying it should be 159.38 hertz. 159.38 hertz. Okay, percentage is 0.25. Okay, that I will change. What else? Dimension is what? 35 GB, 30 GB, 7 GB. That's fine. Should match. Either our dimension is not same. So you have to check the dimension. What dimension we have used here? Okay, it has used S8R11. That's fine. But what is the dimension of this plate? Okay, so 300, 400. So it is okay. 300 by 400 mm. That also I used. 10 mm. That also I used. So now what we have to do? We can do the here we can do the convergence study. Here we can do the convergence study. So what we are going to do? We will increase the mesh size. So first of all, we have to note down. So now we'll go for convergence study. So here we'll increase the meshing. Okay. Increase the meshing. Here we can choose this option. So now this side we can use 40 element. This side and use 40 element. This side also can use 30 element. And here along the thickness we should have at least 4 element. Here at least 2 we should have, and here we'll choose along the thickness we should have at least 2 to 4 element. Okay, 2 to 4 element, so that we can have a deformation along the thickness. Otherwise it will be stiff along the thickness, will not have good result. So here along the thickness we'll have few numbers. So here I am choosing 4. Okay, we can use these options to see. Here we also use 4 element here, this one and this one, not 40, it should be 4. Okay, now again go for meshing. Now you can see we have created a meshing. Now we'll submit the job. Okay, so now here you can see first frequency is coming 165. First frequency is coming as 165. We had here 159. So it is our expected range. Here you can see it is 165. Okay, so now our first frequency is 165. Next we have second frequency is 261. Okay, and 423 and 432, and next we have 539. Okay, so these are the frequency we are getting. Again we have to do one more convergence study. Okay, and see how much value it is changing. So again we'll go for finite meshing and we'll see. Okay, So again here we'll go to the meshing, and again we'll choose the meshing option here. We can choose now, we can choose your, instead of 40, you can use 80 element this side, and here this side also 80 element, this side also 80 element, and use 60 element this side, and then choose 60. Now here we can do the meshing. We'll see how the meshing look like. Okay, you can see the meshing look like this. So what we can do, okay, the meshing look like this. Now again here if we go to the step, here we can control that zero value, that value which is coming zero, that part you can go first 5 mode. Here you can control. Here it is saying that minimum frequency interest, minimum frequency of interest. So since we know our first frequency is coming 165, so I'm writing our minimum frequency is 1. So now what we'll do, we'll observe that in this way we are avoiding the rigid body mode. So here we can go to the job and you can submit the job. Okay, we'll observe that we have no rigid body modes now, since we have chosen our minimum frequency is 1, because first 6 mode was coming 0 frequency, so we don't want that. Initially I run it to run, we have initially run it to see, to learn what is the rigid body modes. Okay, since we do not have provided any boundary condition, it should show some rigid body modes, so that we have learned. So now again you can see first frequency is coming here 159.11, second is coming 261.52, next we have 413.29, next we have 3433, and then we have 532, like that. Okay, so here we will see what are the frequencies coming here. So here you can see it was 159.38, 262, 414, 462, 555. So here you can see our initial frequency are matching. So you can see that our model is correct. Now since we have assumed some parameter which was not defined there, we have assumed some parameter, for example E3 Poisson ratio, we assume 0.15, but here it is mentioned 0.25. We'll change it and we'll see how our result is varying. But before to that, we'll go for one more run for convergence study. Okay, we'll go for one more run to go for convergence study. So here we'll select this, meshing. Okay, we'll select this meshing and select this one. Now here we'll go for 160 element, this side, and here we'll choose 120 element, here 120 element, here we have 160 element. Now we'll go for meshing. Here you can go for meshing. Here you can see meshing is very fine, and our mesh element, each element will look like a square. So it is our well conditioned element. Okay, now we'll submit the job. These are well conditioned element we have used. We have used well conditioned element, and we'll run the program. We'll see what are the result is coming. Since we have increased the element, it will take a little more time and we'll have some converged result. If we observe that our result is changing much, in that case, again we have to go for final machines and we have to perform the convergence study. If you observe, our result is not changing much, it is within our expected result. So, or you can see if it is not changing from our previous result, so we can stop our study, convergence study there, and we have to take some judgment to use number of element there. So here we'll see how much element we should take. Here you can see it is taking more time. If you increase number of element, then your degree freedom also will increase, your K matrix also will increase. So here you can see we have root under K by M. So mass matrix also will increase. So again, there is involvement of inverse of mass matrix. So it will take long time to get the inverse. If it degree freedom increases, then it will take long time to get the inverse. It will take long time to get the result also. So now we got the result. We'll see what the result is coming. So here our result is now 158.7. It has changed little bit, and we have 261.60. Then we have 412.81. Okay, and we have 433.95. Then we have 532.44. Okay, this is our first 5 mode. So here you can see first mode is very close, second mode also close, third mode also close, fourth and fifth mode has some deviation, but since we have used little different property, we have assumed some property of E3 and your Poisson ratio G1323 that we have assumed. Most of the cases you will observe that we are interested on the first few modes. Okay, so if you are happy with the first 3 mode, you can accept this result. One more thing you just observe that here we model it using solid element, but the data from where the data we have taken, they use cell model. So the data we have taken, they use cell model, but both are giving very close results. So here one more thing we'll do, we'll model it as a cell element and we'll see how the result is coming. Okay. So now here we gave a run with your changed Poisson ratio. We will see how our result is affecting. Since we know that Poisson do not affect the frequency much, so you'll observe that that is not affecting much, at least in the initial few mode. Okay, in the initial few mode, the Poisson will not affect much. Poisson ratio might affect on the higher range where we have large deformation. If you go higher mode, basically you'll observe that our deformation of the plate is large. In that case, Poisson may affect. Okay, even our out of plane frequency, out of plane metal property also will affect. Out of plane property also will affect. Okay, since in the higher mode it is deforming large scale, and out of plane metal property may affect. So here we'll go for result. Here we'll see same 158.8. It has changed little bit in decimal places. 158.88. Then we have 261.15. Earlier we have 261.60. Now 261.15. Now we have 414.81. Earlier we had 412. Now we have 441.13. Earlier we had 433. Now we have 533.27. Now you can see it is affecting the frequency which is in higher mode. Okay, so similarly, you'll observe that our young modulus in the out of plane direction also will affect in the higher mode. Here you can choose, here we can change it, here we can change it to 25 GPa. Okay, and you can see it is affecting, but it is affecting mainly in the higher mode. Once we complete this part, one more thing we'll do, we'll change the type of element. Here you can observe, that we have model it using your C3D8R. Okay, next run, what we're going to do, we'll change it. Okay, and we'll give a run. So we have changed it. Next time, once giving the run, that time ABAQUS will take this data, okay, with your quadratic element. Once you give a run of that with the quadratic element, once you give a run with the quadratic element, we can see how our result is affecting. Okay. So now here you can see we are getting the same frequency, that is 158.8 in the first mode, and in the second mode is 261.15, same frequency we are getting. Then we have 414.81, okay, and then 414.13, and next we have 533.27. So basically your out of plane parameter, out of plane your modulus is not affecting much till fifth mode. Okay, it may affect in some more higher mode. Okay, and here from linear to quadratic element, just now you change it. So now we are going to submit this job and we'll see what is the frequency are coming. What are the frequency? What are the frequency are coming? We'll see what are the frequency are coming. Since ABAQUS was taking too long time using your C3D20 element and with finite mesh size, so what we need to do, what I had to do, I had to kill the program. So now what I am going to do, I will choose the number of element. I will define the lesser number of element with C3D20 element and will run the program. See, we have already achieved our convergence study. We know that if we use certain number of element with C3D20 element, we can get composite result. Now, if we want to use higher order element, in that case, your amount of number of element will be very low. Amount of number of element will be low. Okay, so here we are going to choose the less number of element. So here we'll use coarser mesh size, and we'll run the program with C3D20 element. Okay, so here what we're going to do, here we'll choose these options, here we'll choose part here, and now what I'm going to do, I choose these options, seed by age, this and this. Now I'll define number of, here I can make it as a 40. Since we are using higher order element, in that case, we can choose less number of element here. Here we can use 30. Here we can use 30. Now we mesh it. I can see this is the meshing we have done. Now we'll run the program. With C3D20 element. So here you can see from the mesh, you can see we have used, quadratic element, that is C3D20R. Okay, till now we had used C3D8R, but now we have used C3D20 element, and we change the mesh size, and we have run the program. So here we can see how much the frequency is coming. So see, one more thing you have to keep in your mind, that most of the cases will require the first few mode. Okay, first few mode is very important, and we'll try to see whether we are getting converged result, whether we are getting converged result of that first few mode. Okay. Go to the result, and you can see first mode is coming a little bit higher, that is your 163.90. Second mode is your 269, 428, 441, 55550, like that it is coming. Okay. Now here again you have to do convergence study. One more thing you can do, you can increase the size. You can increase the size. Okay, you can increase the size. So 80, you can increase the size to 80 and run the program. And here also you can increase the size. Here you can see you are increasing the seed value. Basically, you are using smaller size element. Okay, we are using smaller size element, and we are using higher order element. So now we'll run the program and we'll see whether we are getting converged result or not. Use cursor element using your C3D20, and we have used, and we have got 163. We have got 163. So here if you use C3D20 element, in that case our frequency is coming in the range of 163.90, 269 and 418. Like this. Okay, so now we have to see now. So what we observe here, when we have used cursor element with your C3D20 element, we have got your first frequency as 163, and then what we did, we increased the number of element, and again we gave the run with C3D20 element. In both the cases we are getting the frequency the same. So basically your cursor mesh size that we have used here, okay, that basically your 40 element on longer side and 30 element in that shorter side, that is enough to get our converged result. Okay, so here we have to take some judgment that which element type you should use.
Now here you can see whether you use C3D8R element or C3D20R element. Both the cases our frequency is coming very close. One is 155 like that, another is your 163. So if you see that error, if you see the error, so you can see how much error is coming. Maybe nearly 5 hertz or something like that. You know, if you see 5 by 150 into 100, if you do, you will observe the error is coming nearly 0.03%. So both the result are accepted. Now, if you want to see, if you want to judge which element you should use, in that case, you have to check both the solid element C3D8R and C3D20R, and thereafter you have to take a decision and you have to proceed for further analysis. Okay, so we'll see if you use a cell element, how we can model it and what are the frequencies coming, how much accuracy is there, and if we use composite as a layer wise, then what are the frequencies coming. Okay, so in the next module, we'll try to learn how to model using cell element and how to model a composite in a layer wise manner. Thank you.
The modes of data, what we can do, you can click here, okay, and you just orient, you just place the element here in that free space, and now you go to the file, then go to the print options. From here you can print the file using color, and TF options, TIFF options. Here you can click on same. So now you can see you are creating a file on the C drive and temp folder. So here you go to your C drive and go to your temp folder, and here you can see your mode save data. Here you can see your mode save data. So here you can see we are getting the mode saves, and we are also getting the frequency in hertz. Okay, so what you can do, you can copy this file and paste in a Word file to make a report on it. Now if you want to delete the meshing, if you want to suppress the meshing, what you can do, you can go to the tool and then go to the common, and then you can use your site here. Now you can have a clear figure of your mode shapes. So this is the mode shapes of the plate. Okay. So now one more thing you have to keep in your mind. Mode shape is your shape indicating what is the easiest way to deform for a structures. What is the easiest way to deform for a structure? So here you can see for a plate with no boundary conditions, for a plate with no boundary conditions, this is the easiest way to deform. So this mode is somehow twisting type mode. This is the easiest way for the plate to deform. Next easiest way to deform is your this shape, bending shape. Okay. So here you can see that mode shape also is related to the energy, modal energy. So modal energy. Now here what we can do, we can change the boundary condition here. We can change the boundary condition here, and we can see how your mode shape is behaving and how our frequency is behaving. So here in the boundary conditions we have two options. Here in the boundary condition you have two options. First option is that incluster option or displacement option. So incluster basically indicating your all the degree freedom are constrained. Okay, all the degree freedom are constant. Here in the displacement conditions you can have a options to choose which degree freedom you want to constant. But if you use incluster options, you will observe all the degree freedom are constant. So what I am doing, I am rotating the plate here, and then I'll choose the area where I want to apply the boundary conditions. Okay, it is asking that select the region for the boundary conditions. So I want to select the region where I want to apply the boundary conditions. So here this whole region I want to apply the boundary conditions. So if you use incluster options, so here whatever the node number, whatever the degree freedom it is coming, they will restrain all the degree freedom of all the nodes. Okay, it will restrain all the degree freedom of all the nodes in this region. Okay, so I just apply the boundary condition here, and what I did, I keep all the parameters same as it is. I keep all the parameter as it is. Okay, now I'll submit the job and we'll see how we can get the mode shapes of your composite plate with your cantilever boundary conditions where one end is fixed. Now here you'll observe that our frequency is changing. Since we are restricting here, you'll observe that our frequency is changing. It is increasing because we have restrained one end. Obviously stiffness is increasing. Okay, since we are adding stiffness at one side, that means we are restraining it. Uh-huh. So here you can see that our first frequency for the composite plate, it is 41 Hertz. Next is your twisting type mode is coming. Okay, first mode is bending mode, second is twisting mode, and then this is also bending mode. Again, this is bending and twisting option is there, and this also one type of bending mode. So here you can see this is the way we can perform our modal analysis of a composite plate under free conditions and fixed freeze conditions. So now how to obtain free conditions in real life? So you can hang the bar using some thread or you can use some rubber to hang it. So again, once you hang it, you have to make sure that hanging part the thread does not contribute much stiffness there. Okay, you have to make sure that your thread or rubber does not introduce much stiffness in the hanging zone. Okay, so you can use rubber, okay, and you can update the free conditions, and you can get the frequencies and you can match it. So best way to match your result is to consider a free boundary conditions in real life in experimental model analysis, and you also should do the same thing here in your computer modeling, and you try to match it. So in this way, what you can do, you can avoid the complexity which is arising due to your boundary conditions. So boundary conditions some cases may not be properly fixed. So in that case, that partial fixity will give you some result, and if you assume full fixity in the final model, in that case you may not get the result. And even if you match the result forcefully, in this case your modeling of the material will be different. Okay, your material modeling will be sufficiently different than our actual model. Okay, so best way is to model in free conditions, and then you should choose different boundary conditions to model it. So here we have learned how to model a composite plate using solid element. Initially, a model using your C3D8 element, and we have done convergence study. And in the convergence study, we have seen that how many number of element is sufficient. And then we have tried to run with C3D20 element, and we have seen that if you are using coarser, if you are using finer element, okay, and C3D20 element, it is taking too long time. So what we did, we just cancel that program and then we run it with less number of element with C3D20 element, and we have obtained that our frequency, and frequency also that also was converging because we have run twice, and that also was converging. And then what we obtain is that frequency which is coming using C3D20 element, that is a little bit higher than the C3D8 element. Okay, so next what we are going to do, we are going to analyze the same thing using cell element, and we have to take some judgment that which element we should use to model your composite plate. The next video. So let me stop it here. I hope you get some idea. Thank you.